So thank you everyone for coming on this really cold Saturday morning. Also, I typically give talks, and I'm happy to have people interrupt me and ask questions, so you don't have to wait until the end if something is like, I'm telling you something and you are really struggling with it. Just raise your hand, and I'm happy to answer the question during the talk. I think that creates a more dynamic experience. So, and I also may ask for audience participation at certain points. You don't have to raise your hand to participate. You can just yell out your answer. OK. So today, I'm really happy to be able to share my research with you. So in my lab, we work on trying to build the building blocks of a quantum computer. And during this talk, hopefully, I'll give you an understanding of what a quantum computer is and what these building blocks are going to be made of. And what we focus on is actually building a quantum computer using aluminum. So that's why there's these, hold on, let me make sure my clicker works. That's why there's these, hopefully you think they're cute cats that are made from aluminum foil here. So perhaps you're at this talk because you've Googled quantum computer and you've seen some interesting headlines. So to prepare for this talk, I wanted to know what was out there about quantum computing. And I found this collection of headlines, which makes quantum computing seem like it's something that you definitely have to know about. So Wall Street is really into quantum computing. It's not, apparently they already know that this new kind of quantum computing is going to shake up finance. And the question is just one. If you go to WebMD, not only will they tell you that you might have cancer from your symptoms, but also that a quantum computer will help you beat cancer. OK. The Independent is a little bit less optimistic. They think that a quantum computer is going to lead to a quantum apocalypse, and how ultra-powerful computers, these ultra-powerful computers are going to cripple governments and break the internet. Wired, so actually Wired has many articles about quantum computing. This is just kind of the two ones that I found first. So in 2020, it said that quantum computing is bigger than Donald Trump. I don't really know what that means. It has a quantum leap in computing is good for the climate crisis. So maybe, I don't, could be. But before you leave this talk with the idea that quantum computing is going to lead to an apocalypse, or I see some headline after this talk that UIUC professor says quantum computing is going to end the world, let's first talk about what quantum computers can do. So these are the three main ways that we think that quantum computers will be useful. So the first thing is that we don't think that quantum computers are going to be able to change everything about computing, but they are going to be able to help us solve certain problems. So I put some of those problems here. So one of the ways is that some quantum algorithms are going to be able to outperform classical counterparts. And these algorithms are actually very special and specific. The most famous one is actually the algorithm that sort of launched the field of quantum computing, which is an algorithm to factor large numbers. And this is actually, it might seem like an esoteric problem, like who cares if we can factor large numbers, but actually all of the encryption that our modern society is based upon is based on the fact that we cannot factor large numbers. And so, and all of our computers, it would take way too long for all the current computers that exist to actually factor these really large numbers. And there is a quantum algorithm that if we could build a quantum computer, we'd be able to factor out these large numbers. So before you think, oh no, we really don't want a quantum computer, it's going to get rid of all of our encryption, we also think that if we were to build a quantum computer, we would have new kinds of communication and new kinds of cryptography. So we could actually build even safer ways of securing your information and encrypting your information. So even though a quantum computer might be able to break our classical way of encryption, we'd get new ways of having encryption that would be much safer. And actually, we don't think anyone would be able to break, or anything would be able to break these encryption keys if we could build one with a quantum computer. So the other thing that I'm really excited about that quantum computers do is quantum simulation. So actually everything is based on quantum mechanics and the interactions between particles that are really small. And it is very difficult for a classical computer to simulate these quantum systems because of these interactions that they have to take into account. And so if we're able to simulate these quantum systems, we can discover new materials, discover new kinds of drugs, and maybe indeed one day, not soon, sorry, help beat cancer. OK, so this is the application that I'm most excited about. So if you decide to leave this talk right now, hopefully you now know what a quantum computer can do and why we're interested in it. But all of these applications require a really large number of high-quality qubits, and we don't have those yet. So what I'm going to talk about during this talk is why a quantum computer is so hard to build, and what we are doing to try to make a quantum computer reality. Okay, so before I start, are there any pressing questions or comments? Okay, so for this talk, what I'm going to go through is first, how does a computer work? I want us to be able to understand what is limiting our current computers and how a quantum computer would be different from our current computers. And then I'm going to talk about what is a qubit. This is the basic building block of a quantum computer and how a quantum computer actually works. And then finally, I'll go into a little bit of experiment about the experiments in our lab and how do we actually make a qubit using aluminum. Okay, so first thing we're going to talk about is how does a computer work? So audience participation time. Does anyone know what the building block of a computer is? You don't have to raise your hand. You can yell it out loud. Yes, so these are all building blocks. And we use transistors to encode information with our computer. So the building block is the information. The way that we encode information is stored in something known as a bit. And we use the transistor to store that bit. So you can think of a bit as two levels. So it can be, we call it 0 or 1. So that's why we have this switch here. And the way that the computer encodes information is that it says, OK, I'm going to have one bit that's going to store it as 0 or 1. And if I want to store larger amounts of information than just 0 or 1, I can arrange those bits in different ways to create, to be able to store all the information that we have in our phones, in our computers, in our apps. And so that's how computers work. So just to go through a little bit how the computer stores that information. So if we wanted to store numbers, 1 is just 1, 2 is equal to 1, 0, 3 is equal to 1, 1, and 16 is equal to 1, 0, 0, 0, 0. Okay, so for the mathematically inclined, this means that our computer stores information in base 2. Okay, so we don't want to just store numbers. We also want to store letters. So if I wanted to write hello to you on the computer, the way that I would store it in the computer is using 8 bits. So I write H as 0, 1, 0, 0, 1, 0, 0, 0, 0. I'm not going to read out the rest of these because they're really long, but this is how you would store letters. Okay, the last thing that I think is interesting is how our computers store images, which I think a lot of you have photos in your phones. And then so the way that we store images is that each image is divided into a pixel. And if I want a grayscale image, then I actually just need 2 bits. So I'm going to associate 1 with white. So that if it has two ones, then it's pure white. If it has 2 zeros, then it's pure black. And if it's somewhere in between pure black and pure white, then I'm just going to have it be 0, 1 or 1, 0. And so if it's closer to white in the gray, then this number is larger. And I'm going to have 1, 0. And if it's closer to gray, then it's going to be 0, 1. And if you want to store color, we need way more numbers because there are way more colors. So there's usually 256 colors at least that you can store. And then so you get 8 of these numbers corresponding to a single pixel, and then you can write down your color associated with that pixel. So that's how images are stored. OK, so we don't just want to store information with our computers. We also want to be able to process them. And so what we do when we're processing is we use something known as gates. And then so microprocessors have lots of gates in them. And then so the idea with the gate is that we take some input to our computer. So we have these 1s and 0s again. And then we take 2 inputs. And I have a gate this is called an AND gate. This is typically the symbol for a gate will typically look something like this. It can be rounded or it can be sharp. And that will tell you that it's a different kind of gate from the AND gate. And so if you want to process using gates, you add 2 bits in here, and then you get a truth table out that tells you that if I put in 2 bits of a computer, input 1 and input 2, if they're both at 1, then the output is going to be 1. And if input 1 is 1 and input 2 is 0, then the output is going to be 0. And if I only have 0 input 1 and input 2, then I get 0 as an output, and if both are 0, then I get 0. So they're different kind of gates, and they provide truth tables that look like this for the inputs, and you can combine them to perform many different operations. Okay, so this is the basis of all of our computers, and our computers, our supercomputers that currently exist, are extraordinarily powerful. The UIUC actually is home to multiple supercomputers. One was just decommissioned last year. It was known as Blue Waters. So this supercomputer was capable of more than 13 quadrillion operations per second. So that is an incomprehensibly large number, I think. This is what it looks like written out. And then a CPU on this supercomputer failed about once every 3 days. So it could perform 13 quadrillion times, so they're about 4,000 seconds in an hour, and then 24 hours, so 80,000 times 4, so 240,000 times this very large number before you had an error there. And so our current computers are actually extremely good. They don't really have any errors that happen, and we can analyze really interesting and important and large problems with a lot of data using our supercomputers. So some research examples that use Blue Waters are, for example, there's something known as marginal land in crops. And then so marginal land is land that you can't build crops on. But it turns out food crops on. But it turns out you can grow bioenergy crops on those. So they can still be used for, to produce something for us. And then so there was a research problem where they used Blue Waters to analyze 9 billion pixels for each year of 8 years of satellite data. And from that, they found where there was marginal land that could be used for growing bioenergy crops. So 9 billion pixels. So remember that little picture that we had? That was, I think, 16 by 16 pixels. And so 9 billion times 8 of those pixels were analyzed using Blue Waters. So that's really a huge amount of data that was processed using Blue Waters. We've also, from a physics standpoint, it's also been really useful to have Blue Waters present on UIUC. So one thing that people are looking into is something known as dark matter, which exerts a gravitational pull on the stars in our universe. And then so using Blue Waters, they were able to calculate data for about 1/8 of the entire sky that we can see to identify where there might be dark matter in the universe. And finally, there was some problem. I mean, this is just a small smattering, but I'm listing some of the ones that I find cool here. There was a group that was looking into diagnosing multiple sclerosis and Parkinson's disease based on the gaits of people. And then so this is actually a huge amount of data because you're analyzing video and looking for small, subtle differences in the walks of people who might have MS in the future. And by looking through that data, they actually found that they could correlate a small difference in someone's gait with the diagnosis of MS and Parkinson's disease. So this is just to tell you that our current computers are extremely, extremely good and can process a huge amount of information. But there are some problems that our current computers have difficulty with, and I've listed 4 of these here. So one of them is searching through databases. So if you have a database with n entries, every single classical computer is going to need, on average, n questions to this database to solve, to search for the thing that you want. It might get lucky, and it might be less than n, but on average, it's going to need about n queries to find the database, to find the thing that you want in the database. It's also quite difficult for classical computers to simulate complex molecules. So if you have a molecule that's formed from all of these different atoms, and they have bonds in between them, you also have to consider the interactions between all the atoms that don't have bonds in them. So there's a lot of interactions that have to take place, exponentially many actually, as you increase the number of atoms in this molecule, and it makes it really difficult for our supercomputers to be able to solve molecules that are more than 100 in atomic size. Again, so I mentioned factoring large prime numbers. That's also really difficult for computers to do, because once you get to a really large number, it just basically has to try all of the factors going up to that large number to find the right factors. And the last thing that is quite difficult for computers to solve is systems of equations. So this you can actually do with just your calculator, but for systems of equations that are much larger than this, it's difficult for a computer to solve. And then so these might be just seem like kind of random problems to you that are not relevant for us, but they actually are very relevant in our daily lives. So this is basically used whenever you search for anything. Whenever you use Google, whenever you use DuckDuckGo, or whenever you use Bing, it's searching through some database of information. So simulating complex molecules is very relevant because we need these to find new materials that might help with drug delivery or they might help with solving some chemistry problems. And so we actually do need to understand very complex materials and the interactions in them to be able to find new materials that we can use to move our technology forward. This, as I mentioned, was the basis of modern encryption. And then also, so solving systems of equations, they're used actually in many different types of optimization problems. So say you wanted to get from one place to the other, and you had lots of different options for doing that, like taking a train or taking an airplane or taking a taxi. And you want to find the fastest way, and you can actually represent that problem using a system of equation. And then, so try to optimize based on that system of equations. So it's very useful for optimization, which we use a lot in our modern lives. Okay, so it turns out I am a quantum computer. I work on quantum computers, so I've chosen these problems such that there are quantum algorithms that can do better than our classical computers for solving these kinds of difficult problems. So a quantum computer is not going to be able to solve every problem better than a classical computer, but these are some specific problems that a quantum computer could do better on. Okay, so we can now start to talk about a quantum computer and start to think about how we can actually try to make our current computers better. And then so one way is that we can try to make our single bits a little bit more powerful. So instead of just having two levels, so instead of just having a switch where I can just be on or off, I might imagine that I want to create a building block which is like a dimmer switch, right? So maybe I want to, if I can create something that's like a little bit on and a little bit off, or a little bit off and a little bit on, as you might imagine with the dimmer switch, then I might be able to increase my computing power. So this is a new type of building block that we can use to try to increase our computing power. And we can also try to increase the number of gates that we have that our computer uses for processing. So this is the list of all of the current, well, not all, there's a couple more, of current computer gates. These are the most common ones that our computers use. So I showed the AND gate previously. There are also other operations that our computer can do. So these are our current computer gates. If we increase the kinds of gates that we can do, if we add new gates, maybe we can increase the processing power or do different processes. So these gates can only be done on a quantum computer. You can do a rotation. So if I have my little dimmer switch, I can move it around with my rotation. That's what this would do. If I have multiple dimmer switches, so that's what these kind of lines represent. So here I have 2 gates, here I have 2 gates as well, here I have 3 gates. What you can do is actually change the state of one of your dimmer switch depending on the state of your previous, depending on the state of another dimmer switch. And this is something that is unique to a quantum computer, and you can't do this classically. So these are new gates that would be possible with our new building blocks. Okay, so this was kind of a general introduction to computers. So our current computers, we use them all the time. But if we build our little quantum computer that's made based on these kind of dimmer switches, it's actually as if we are trying to do our computation in Illini Stadium after we've won a football game. It is extremely, extremely hard. People will knock it over, and we won't be able to do our computations. So if we build these new building blocks and just kind of leave them out in just like the environment, like leave them out where this computer is, for example, it will not be able to do any computations because it'll basically just get kicked over. It'll feel like it's done here. And then so quantum computer scientists are actually extremely paranoid people. We want to try to build our quantum computers, but we would need to hide them from the environment and from anything that might walk into it or kick it, so that it's actually able to do this, have this new processing power that I'm discussing. So the next part of my talk is going to discuss a little bit more concretely what this dimmer switch kind of looks like and how we use it. So before I move on, are there any questions about computing or anything like that? It was starting to get out of date. So actually at NCSA, they have a new supercomputer. It's called Delta, and it has more computing power and actually lower error rates. So it's just that we upgraded Blue Waters, basically. You can think of it that way. Any other questions? Yeah. Blue Water's not being used at all? I think that it is not being used at all, yeah. But I don't work at the NSCSA, so, okay. Okay, so in the second part, I'm going to discuss what a qubit actually is. So our dimmer switch, how we represent it is actually, so we had this 0 and 1, and then so that was the on and off for our switch previously. But now our dimmer allows us to move anywhere between our 0 and 1, so a little bit on, a little bit off. And then so the way that we represent that we can do that is by using a sphere here. And then this vector, this pink vector, points in the direction that we want to say that we want to store our information. So I can point my I can go to let's say 3 on my dial, and then this vector would mean that I've gone to, the location of this vector tells me that I've gone to 3. And what I can do to represent that is I can represent the state of this vector using a capital psi, and that tells you, and I can write it as some amount is in 0, so alpha is in 0, and beta tells you how much of 1 the state is in. So I'm in both 0 and 1. So if you've ever heard of someone saying that Schrodinger's cat means that the cat is both dead and alive, let's say the dead cat corresponds to 0, and the live cat corresponds to 1, and there's some probability that it can be in those states. Okay, so this is what our qubit, or our quantum bit, is going to, how we represent it mathematically. The only problem is, which I mentioned with imagining that our dimmer switch and we're trying to do our processing at an Illini game, is that if you look at our qubit, and by looking, I mean just something walking into it, something as small as a photon coming from the light in this room, just seeing it a little bit, or an atom walking into it, it immediately goes back to being a classical bit. So so your dimmer switch, it's like magic. Your dimmer switch immediately goes back to being a two-level system. So you lose all of that computing power that we were talking about. So we need to be able to maintain these really fragile superpositions when we're building our qubits. And also, we need to be able to manipulate it without looking at it. Okay, so this might seem crazy. Can I just finish my sentence and then I'll answer your question? Yeah, so this might seem crazy, but if you ever imagine that in your house you've had a dimmer switch for a really long time, you can probably turn that dimmer switch to the right setting without looking at it. This is kind of what we do when we're trying to build out a qubit. We study it a huge amount so that we know what its behavior is going to be and try to control it so that we know what its behavior is, so we don't actually have to look at it to set it to the right place. Okay.
So for the psi,
yes.
for a qubit, are the alpha and beta, do the alpha and beta have to be related?
No, they can be, yeah, so they have to be some percentage. The percentage has to add up to 1, but that's the only relationship that they have to have. So that's actually a really nice segue into my next slide, which is that if I'm able to produce this psi multiple times, I can actually measure it many, many times. And each time I measure it, I'm either going to get 0 or 1. And the probability that when I measure it, I get 0 is going to be alpha squared. And the probability that I get a 1 is going to be the absolute value of beta squared. And so quantum bits are different from classical bits in that when we measure them, we don't exactly know where they're going to end up. We know with some probability where they're going to end up. Okay, so that is a quantum bit. Now we can talk a little bit about what we need to do to process these qubits. So the idea is that I want to have multiple qubits, right? If I want to one day do 13 quadrillion operations, I'm going to need a little bit more than 1 qubit. And then so I have all of these that I now want to be in some superposition. And then I want them to have some interaction, so that's what these purple lines are. So they want them to have some interaction with each other. And the idea is that I actually cannot look at this. I can put it behind, I need to put it all behind some black screen, so I'm not looking at it, not measuring it, so it's able to maintain its superposition and do its processing. I'm allowed to not look at it and go in and move it around, but I'm not allowed to look at it when I'm doing this processing. And no one is allowed to look at it while I'm doing this processing. So no photon, no atom, nothing can interact with it while it's doing the processing. And then once it's done, then I know after it's done doing all of these gates and the things that I want it to do to solve my problem, then I can come back and measure it. And the idea of quantum computing is that for a specific problem, we can perform these gates, so that's these manipulations that I'm going to do without looking at it, such that at the end of the computation, the probability of measuring the correct answer is really big. We have some probability of measuring the wrong answer, but that's going to be small. So we might need to run this algorithm multiple times to actually be sure that we're getting the right answer. But the probability that we're getting the right answer is going to be really big. And then once we have that right answer, it actually turns out verification is a very easy problem for a classical computer. So once we give it the answer, like if I want to factor a prime number and I give it 2 factors, it can just multiply that. So that's fairly easy for a classical computer. So we would use them together to actually increase our computing power. And then, so this is what we want to do. This is how we use our qubits for processing. Turns out, though, if you thought measuring, and then once we measure, they're all pointing in the right place, so our probability of getting the right answer is big, and probability of measuring the wrong answer is small. If you imagine what I said before, so 1 qubit is extremely hard to build because something is always trying to run into it and ruin its superposition. You might imagine that using multiple qubits becomes even harder, right? Because now I have lots of things that can go wrong. So I have now for this, it's just a 2-qubit gate. So I have these 2 qubits that are in superposition. So now 2 things that can be looked at. I also have this interaction that also turns out to be extremely fragile. And then so if something looks at that, they can also destroy the interaction as well. So I have all of these things that are trying to look at my qubits and cause them to no longer work. So this is a problem that we face when we're trying to build a quantum computer. There is always something that's trying to look at our qubits, trying to ruin our gates. And so as you might imagine, quantum computer scientists and quantum physicists that are working on building quantum computers are extremely paranoid. We are extremely paranoid about anything running into our qubits. And then so one of the problems that my lab works on is trying to figure out how do we build these qubits such that we can still kind of go in and manipulate them without looking at them while keeping everything away from observing them. So eventually we want to do something like this. So on the left is actually showing you the gates that we want to apply on our quantum computer. So this actually has 4 qubits and 5 qubits that are represented by each line and the different gates that we want to do. And I've sort of highlighted what the gate does at these dashed points to the individual qubits. So I want to be able to start. I want to manipulate my qubit to be in a certain place. So I have to do all this. All this has to be done blind until I do my measurements. So all this is behind some black box. And so I want to be able to send my qubit into a specific state. I want to do that, send it to a new state in my second step. Then I want them to interact with each other in some way. And then I want them, during this interaction, to work together such that when I do my last step and then when I measure, I'm going to get the right answer. So this is, to build a quantum computer, we need to be able to do all of these steps without having errors, without having people or anything in the environment look at our qubits. So this is the problem that we're trying to solve. And so now maybe did you have a question? Yeah. If they're facing each it depends on whether you have some interaction between them. If they're totally separated and just facing each other, that just means that they're facing each other. If they're interacting with each other and facing each other, they can change the behavior there's some interaction, so they can change their behavior. And they might move in the same way or move in opposite ways. Yeah. OK. So I've told you that we're very paranoid, and that one of the things that my lab is working on is how do we build better qubits. So if we sort of think about how you would try to make your qubit less sensitive to the environment, we want to try to make our qubit invisible, basically. We want to make it so that you can walk through it, or if you kick it, you won't feel that you've kicked it, right? And then then the qubit is not affected by whatever you do. And then so we try to make our qubits less sensitive to the environment. Another option that we actually take both of these options, is to put our qubits into basically what are safes. We put them into a place that can't be accessed by anything. So we have special vacuum chambers where we pump out all of the atoms and all of the molecules and cover it so that light can't get to it either. And then so we protect our qubits in multiple ways. And so, yes? That is an excellent question. So the question was, how do we eliminate the naturally occurring radioactivity? So what we can do is actually there are processes that you can, like annealing or other things where you can drive out any kind of ions that are causing this naturally occurring radiation. Or you can use certain materials that don't have that radiation. So if you use like very old lead, then that radiation does not affect our qubits. Yeah? Yes, it does affect them. There are actually multiple experiments trying to quantify the effect of gravity on our qubits by sending them into space and then seeing what the effects of having a differing amount of gravity on those qubits would do. Yes? Yes, that is also an excellent point. So the material system that I work with is a superconductor, and the superconductor needs to be very cold in order for it to be a good qubit, and we'll talk about this in just a little bit. And then so for the superconductor, if a cosmic ray hits the superconductor, it's like it's getting very hot because that cosmic ray hits it. And then so cosmic rays are also very bad for our qubits. So I guess the answer to all of the questions are yes, all of these things are very bad for our qubits. Okay, so now I'm going to be a little bit more concrete about the types, how we actually build these qubits. So I've chosen, there are a few leading platforms for building qubits, but I've chosen just kind of 3 of them. 2 of these are represented here at UIUC, and yeah. So one way in which we store so we remember we want to find a system in which we can build this kind of dimmer switch, right? We want to have a system that has 2 levels, so it has a 0 and a 1, and we're able to move in between those 2 levels continuously. And then so one system in which we can do that is something known as a trapped ion. So an ion has some electrical charge, and then so that electrical charge is what we use to actually move that dimmer switch. And we store the state of our qubit. So 0 is going to correspond to one energy state corresponding to this orbital of the ion, and 1 is going to correspond to this orbital, which is slightly higher in energy than this red state. And these trapped ions actually are able to do 10,000 operations, which is not 13 quadrillion, but 10,000 is pretty good, operations before you get an error. And the way that we can do that is actually these trapped ions are located in basically an extraordinarily good safe. It's inside a vacuum chamber where the pressure is 10 to the -9, so that there are no atoms or molecules that are going to hit it. It's also extremely well shielded inside of these vacuum chambers so that there's no electric field or magnetic field that we don't want interacting with these trapped ions. Another way in which we build qubits is by storing the qubit in an electron spin. So what you can do is you make a very pure material that has electrons in it, and then we can apply an electric field so that the electron gets in this material and doesn't interacts very weakly with anything else. And then you store your information in the spin of the electron. So a spin of the electron pointing up is 0, and the spin pointing down is going to be 1. And then by changing the electric fields that are on these little metal pieces that are affecting your electrons, you can manipulate these electron spin states. What I work on is superconducting qubits. And superconducting qubits are based on superconductors, which we'll talk about in just a little bit. And the superconductor is we can make circuits out of superconductors. So I can make an inductor, or superconductor is actually based on a metal. And so I can make an inductor. I can pattern that metal to be an inductor or a capacitor or something known as a Josephson junction. And then I can store my information in the direction in which the current flows in this circuit. So I can store it in the current flow. I can decide my 0 is going to be the current flowing clockwise, and 1 is going to be the current flowing counterclockwise. So those are going to be my 0s and 1s. Okay, so before we move on, I'm going to specifically talking about qubits made using superconductors, so made using aluminum. Are there any questions about anything?
I suppose you're going to answer this, but with the superconducting, 1 to 0 would be the direction of travel. How do you make it partially 0 and partially 1?
We put it into a we put it into a superposition of exactly that something is tunneling coherently so that we can actually be in direction going in both. The current is actually flowing both ways. So if you were to measure it, the average of the current is 0. But if you were to be super fast and be able, but if you were to measure the direction of the current at any given time, it's pointing left or pointing right. But it's able to go in both directions. Yeah. Okay. Any other? Yeah. Yeah. Yeah, so the way that it works is, so with 0 and 1, I have to do digital processing. I can't, if I have a superposition, what I can try to do for those specific problems that I'm talking about is you can have that superposition, you can think of it as like a wave, and then I can have the waves interfere with each other and get the correct answer. So what if I have a superposition, then I can sort of occupy more, let's say, more of the computational space. And then I never have access to that computational space while I'm occupying it. But at the end, I can try to like push my computation to the right place at the end. So the fact that you can cover more of the space while you're doing the processing is what gives you a little bit more power. Yeah. Any other questions? OK, so now we're going to talk about how do we make qubits using aluminum. OK, so just so we're on the same page, I'm going to talk a little bit about metals. And I actually have a demo that shows this. So a metal, you can send a current into it. And typically for a normal metal, you'll measure some resistance. And then so if I think about what is actually happening microscopically in this metal, when I send in this current, the electrons in the metal, which are represented by these green circles, are being pushed by the current. So they're carrying this current, and they're moving in this direction. But inside of the metal, there are some little defects, some little things that are not, that these electrons can scatter off of. And then so the resistance that you measure is actually due to the fact that these electrons are scattering off of these defects. So for just a visual aid, I have a little demo that I'm going to show that just shows you what is happening. Oh, that's not the demo, but for right now. OK. Right, so, and if I try to store my quantum information in these electrons at this point, it's a really bad idea, right? Because as soon as any electron smacks into one of these defects, it's going to lose the information and not be able to process. So a metal is not a good place to store your quantum information. And then so the demo is just to show you kind of what's happening. So if I think of this material with a bed of nails as my metal, and then I have these electrons, I lost one. That's fine. And then I now let my electrons try to flow by applying a current. You'll see that there's a lot of scattering off of everything many times. Right, so if I try to store my information in these electrons, they will scatter off of all of those defects, and I'll lose my information. Turns out, though, that if you cool metals to very cold temperatures, so in a fancy refrigerator that gets down to very cold temperatures, you will be able to, how cold. There are, for metals, I think the highest metal temperature is around 9 Kelvin, which is, 9 Kelvin is 282, so I don't, minus 200 Celsius is the temperature that you have to cool it down to actually get this kind of behavior that I'm going to discuss. Yeah. OK, so super, super cold. Very, very cold. So that's why we need fancy refrigerators, not just the ones that we have at home. OK, so what it turns out to happen is that if you cool down the material, I will show you actually a demo of that in just a second. If we cool down something that is a superconductor, if we cool down our metal in these dilution refrigerators, the electrons turn out to combine into one state together, and then the entire material just behaves as if it's one giant object. So even though there's these little defects inside of the material, if I now try to send a current into the material, and then have the electrons flow, there will be no resistance because this slab just behaves as if it's one object, and it doesn't feel like the electrons that are all acting as one object don't feel these defects. And then so this is kind of this idea of being insensitive to being measured, right? So now I had these electrons that used to scatter off stuff, but now when I cool it down to very cold temperatures, all the electrons condense into just one giant phase, and then they all move together and are not sensitive to the defects that are in the material. And then so we actually this is, UIUC is the location of the founding theory of superconductivity. So one of our professors here, Tony Leggett, had the idea for explaining how this actually occurs in a material called helium-3, which acts as a superfluid, which again has electrons that cool down and can basically just behave as one single object. And then so this thing that is now no longer sensitive to defects turns out to be a really good thing to store a qubit in. So to show you just how cool that cooling something down into and having it become a superconductor is, I have this demo of a superconducting material. So I'm going to just change my slides to show you this demo. Okay, so here I have a material. It's at room temperature. It will become a superconductor, spoiler. But right now it doesn't do anything. I just put it on here and it kind of just is there, okay? So now what I'm gonna do is put on my safety gloves because I'm being filmed and also a picture is being taken of me. So I'm gonna put on my safety gloves, and then I'm going to take liquid nitrogen and pour it into the styrofoam, which is a good insulator, so it means that the liquid nitrogen is gonna stay there. So liquid nitrogen is really cold. It's at 77 Kelvin, which is minus 200 Celsius. And then I'm going to put my superconductor into this little thing because I don't want to put my hand into the really cold liquid nitrogen because that will freeze my hand and then it will shatter off. So I'm going to now start to cool down this superconductor. And then so the liquid nitrogen is boiling because I'm putting a hot object in contact with a cold object. So it's heating up the liquid nitrogen and making it boil. And I just want to wait until it stops boiling. Because that will tell me that the superconductor is no longer hot. And then so it probably is now a superconductor because it's been thermalized to the liquid nitrogen. Okay. I'm a little bit impatient of a person. So, but I'll try to be patient so this demo actually works. Okay, so let's try. So now, I have these gloves on. So now, can you see that it's floating? Yeah, okay, so now I have a bank of magnets here, and this bank of magnets, it's generating some fields, and then that's going to, if I spin, oops, that was too much force. Okay, so we're gonna get it to float again. Okay, and then it will just follow that bank until it gets warm again. So that is one of the defining properties of a superconductor. It's actually one of the properties that tells us the electrons that have cooled down and are acting as if they're one object. So what's happening is that there's a bank of magnets down here, and it's creating a field that's trying to go into the superconductor. And the electrons really don't like that, so they all act together to oppose that field. And then so the little magnetic field creates a bubble in which this superconductor is sliding around in. And then so as long as that superconductor stays cold, it's going to keep going around that track. So that is dependent on like the humidity and the temperature in this room. So I can't give you an answer right now. By the end of this lecture, it will be warm. Okay, so that is just demonstrating that our superconductor, when we cool it down, it's gone into a different state. So before, remember, it was just staying on top of those magnets, wasn't really doing anything unique. Now the superconductor, the electrons have condensed into this state where they're all they're all acting as one object to oppose this magnetic field. And then so that's why it's floating around the track. Okay, so any other questions? Okay, then I'm gonna go back to the lecture. Okay, so now we have superconductors. Actually, having a giant blob is not very useful because we can't manipulate it. So, but superconductors are metals, and then so we can actually pattern them and make circuits out of them. And then so what we do is we take our giant blob, and then we make a circuit out of it. So our circuit is looking like this. So we're gonna have, I'll actually show you what it looks like in a couple of slides. So our superconductor, we're gonna pattern so that it makes an inductor. So that stores magnetic energy, and a capacitor, and something called a Josephson junction. And this Josephson junction is going to be made from aluminum, aluminum oxide, and aluminum. So aluminum, hopefully, is, or maybe actually, if we're being environmentally friendly, we don't use them in our house anymore. But in the past, we had aluminum in our house, and what we use for our superconducting circuits is actually a very pure form of the aluminum foil that you have in your house. So it's aluminum, aluminum oxide, and aluminum. This is the most math-heavy slide of this entire talk, so just bear with me for one slide. Okay, so this Josephson junction is going to have some energy associated with it, and that energy looks like cosine of phi minus phi external. So phi is can be used to describe what is happening with the superconductor in this material, and then phi external, if I apply a magnetic field, the superconductor doesn't want any magnetic field in it, and then so it's going to try to essentially to oppose that magnetic field. And then so that is quantified by this energy term. And then so the energy in any physical system, it's going to try to minimize the energy. So it's going to try to make this cosine number, because it's a negative number, as large as possible. So it means that in here, the circuit will try to make a 2 pi. So if I apply any magnetic field to this circuit, it's going to try to oppose it with a current. And then so current is going to flow if I try to apply my magnetic field. And that's the direction that I apply my magnetic field will determine the direction of current flow. And so if I change my magnetic field direction, I can change the direction of current flow. And if I do this smartly, then I can store my qubit states in the direction of this current. And that's how we build qubits out of superconducting circuits. So this is one type. There are actually multiple types, but I'm just gonna focus on this also because I'm very much running out of time. Okay, so in the last couple of slides, I'm just gonna talk about how we actually do our experiments. So simplified version is that what we do is we have a computer, and then we go in and we decide, okay, I want to build this type of circuit to build a good qubit. And so, or I want to build this type of circuit to do something else with it. So we go into our computer and we decide, okay, this is what our circuit, we want it to look like, and then we want to print out that circuit so that we can start to measure it and use it. And then so we don't have a printing press that looks like this, but we do have grad students that are good at what they do. And then so they are the ones that make these superconducting circuits. And the way that they do that is that we start with very clean sapphire. This is the substrate that we're gonna put our circuits on. And then we deposit very clean aluminum onto it. And then so once we have that very clean aluminum, then we want to pattern it into some sort of shape. Then what we do is we put a mask on top of this aluminum. So we can, whatever shape we want to make in the aluminum, we put little holes in this mask so it protects it. Everything that's covered in pink is protected, and everything that's not covered is open. And then we etch away the aluminum that's not covered by the mask. So what we end up with, if we have this pattern, is then we have aluminum in all the regions where there's pink, and no aluminum in the regions where the pink has been removed. And then so this is this is a mask, and then so our end pattern is going to look something like this. And then we can change these shapes to be not just rectangles, we can make them like squiggly lines, so they make some inductor. These rectangles will make capacitors, so these are metal blocks that are on the material. So if you want to do this at home, you can take not build a qubit, but like if you want to pattern your metal, you can just you can essentially make holes in your aluminum and make shapes out of them. So that's what we do here when we're doing the metal etching. And then we do a similar process to make even smaller features. So these are on the order of They're less than a micron. They're about 100 nanometers in this dimension. So your hair is about 80 microns. So this is about 1,000 times smaller than your hair. It is the size of our Josephson junctions. And then, so once we do all that, we end up with a circuit that looks like this. So these are these small Josephson junctions that are, which we then put into a copper shield to protect it from the environment, also to allow us to send signals to process it. And then we shield it because we're very paranoid and it's very important. So then what we do is we put our superconducting circuit inside of an absorbing foam so no light can get to it. And then we also put some metal around it so any light that could have gotten to it is reflected off. Then we put it into another shield that gets rid of any magnetic fields that might interact with our device. And then so there's no magnetic field that changes our qubit. And then we put it at the bottom of a dilution refrigerator that is cooled down to 10 millikelvin, which is 100 times colder than outer space. Outer space is roughly, it's actually 2.7 Kelvin, so it's about 3 Kelvin, or the temperature that we operate at is much less than minus 456 degrees Fahrenheit. Okay, so this, you might think that this was enough shielding, but it is not. So we add even more shields. So we add copper shields here at our fridge, and then we add another shield, and yet another shield, and then another shield again, and then this is finally at the outside. This is finally now what you would see if you walked into my lab. And then once we have this, we can pump out the system so now there are no atoms or anything else interacting so that we can get down to very cold temperatures. And this is what you would see if you walked into my lab. So now it's inside of our safe and well shielded, and then we can start to measure it. So what we do is inside of this, we can send signals into our device, and then what we have is we have, let's say, our superconducting qubit that's located here. We can send in a signal to excite it. So it's going to get excited. And then now we can, while it's doing its processing, it's going to do that. But then we want to measure it, and then we send in another signal to go out and measure it. And then that's how our measurements work in the lab. And so this is starting to get to the end of my talk. So this is how we build superconducting qubits. Some of the problems that we're looking at now is how do we connect more qubits together without increasing error? So IBM has actually just announced a 432 qubit device where they have different layers for their qubit readout and wiring so they can isolate the qubits from measurements and from different environments so that you can have many qubits without having errors and losing all of their superpositions. Another question is how do we make even better qubits? How do we make ones that are as good so that we can do way more than 10,000 operations before we run into any errors? The other question is, so your computers, you access servers that are hundreds, thousands of miles away when you're using your computer. And how do we actually do that with a quantum computer? So how do we have a quantum computer that's located in one place and communicate with maybe a server or something that's many thousands of miles away? So that's also a research problem that we're working on. Okay, so and finally, this research is actually, it's an important problem to solve a quantum computer. So there are lots of places in the US and also internationally in which their companies and universities are working separately and also together to try to build a quantum computer. So that's the end of my talk. Hopefully you have some idea of how quantum computers work, and I'm happy to answer any more questions if you have any. Yeah.
So if we ever get room temperature superconductors, would that help you?
Maybe. So we'd have to, so remember I mentioned that we have to understand well how to manipulate these. So if we had room temperature superconductors, we'd also need to understand how to manipulate them and use them. So I think room temperature superconductors would solve energy problems for sure. But it would take a few more steps of research before they could also help with building quantum computers.
So is the need for the extreme cold for the superconducting part?
Yes, yeah. The extreme cold is for both, actually. So if it's extremely cold, it means that so what temperature actually means is that there are things that are kind of moving around you. And then if you cool it down, these things freeze basically and they can't move anymore. And then so if we go down to very cold temperatures, there's like nothing moving around our qubit also. And then so it's also kind of related to shielding.
So you'd still need extreme cold temperatures even if you had a room temperature.
Maybe not as extremely cold. Yeah. Yeah.
So I brought my piece of aluminum this morning, but I didn't bring any sapphire. And those two materials are very specific.
Yeah.
How did you guys decide on those two materials to build the circuit?
Yeah, so for the superconductor, if the superconductor is isolated and by itself, it doesn't have kind of this, isn't affected by scattering, but the issue is that if you start to build circuits out of them, you get interfaces in between that are not superconducting. And then so that it creates like defects that the superconductor will start to feel. And then so when we try to build our qubits, we choose the material that the superconductor is resting on to be extremely pure and free of any problems in the material. So sapphire is one of the materials that you can buy that's extremely pure and won't have any problems. And it creates a nice interface so that you can rest your superconductor on top of it. So that's how we choose the material. Yeah. Yeah.
What's the largest number of qubits in a supercomputer today?
I think actually it was this one by IBM, this 432 qubits one. Yeah. Yeah.
I often hear people say, I'm a computer programmer, and I'm writing a program.
Yeah.
What is a computer program?
Yeah, so a computer program, when they're writing the program, it's at a much higher, there's different layers of computing. So when you're writing a program and there are words in the program that you can understand, that's basically the highest level of programming. So it's an instruction sheet that you send to a computer. So if you go one layer lower, there's something known as assembly code. And then there's some translator that moves from those words that you understand when they're programming to that assembly code. And then it tells your computer which gates, those gates that I was mentioning, it should apply on the bits that it has. So when the computer programmer is writing an instruction sheet for what the computer should be doing. Yeah. I'm going to do this thing. OK, so yeah. Yeah. Yeah, so the question is, if we were free of defects in our metals, 100% free of defects, whether we could also build qubits out of a regular metal. And the answer is yes. So there may be other things that would cause it to decohere, like the interaction of the metal with some random magnetic field that you don't know about or some electric field that you don't know about. But those defects are a big problem, one of the main problems with using regular metals. Do you have a question? No? OK. Did anyone else here have a question? OK, you had a question.
IBM's got like 400 qubits. How many qubits are you really trying to get to really have a
It actually depends on the quality of the single qubit that you have and the quality of the individual qubits that you're using to make your large chip. So if the quality of the single qubits is extremely good, so if I could do 1 million operations on my single qubit before it creates an error, and even when it's incorporated in these big chips, I would need fewer to actually build a quantum computer. But if I could only do like 1,000 operations, then I need to way more qubits to actually build anything useful out of it.
So theoretically, if you had a good enough qubit, you could only use one?
You need at least, I don't know the at least number, but you need at least 2 to 3 to do these gates that I was talking about. So just having one is not enough to do the processing that I was mentioning. Yeah. Yeah. I think that the internet came about actually due to a research. So I am not good at history of physics, but I think that the internet came about actually because of a big research problem. So at a particle accelerator, they were trying to communicate with each other across this very big particle accelerator. So they didn't necessarily want to just have two computers next to each other, and they needed to have communication across the large accelerator so that you could get data on at two different locations. And I think that's how the internet started. But I'm not good at history of physics, so, or history of the internet. So someone else will have to answer. Yeah.
What is the material that the iPad is made of?
Aluminum.
Okay, so aluminum.
Yeah.
That's the premier.
We also, the material can actually be aluminum or niobium. The junction itself that we know of currently has to be made of aluminum, aluminum oxide, aluminum. Yeah. Yeah.
How does the feature size of a computer compare to the feature size of a semiconductor, like a microprocessor?
Yeah.
Today?
They're actually quite close in size because when you try to build for microprocessors, they try to increase the computing power by fitting more and more of them onto a single chip, right? And then so they're actually starting to get quite comparable in the size. So around a few hundred nanometers up to like a few hundred microns for the size. Yes?
Qubits have to deal with the same issues as semiconductors in terms of putting so many on a board. That, but more for us.
Yeah, so the idea is actually, so this previous thing that I was talking about where we were trying to think about the way to make it modular, it's where you could have them communicate, like two chips communicate separately. That we probably will also try to put a bunch of qubits onto the same chip, but if you can have them communicate modularly, that kind of makes the problem a little bit less hard. Yes? Oh, it is much, well, depending on the platform that you use, it is, can be comparable in terms of speed, or it can be about an order of magnitude slower. So it's slower, yeah. Yep.
With normal processors, we talk about a clock speed.
Yeah.
Is there a clock in a quantum computer?
So a clock speed essentially tells you how fast the computing can go, right? Yeah, so here what we talk about is like a gate time. So how fast we can do one of these like interactions that we were talking about. And then so a gate time for a superconducting qubit is around 20 nanoseconds. So in terms of clock speed, now I have to invert, it's, so 1 over 20 is 0.05. So like 50 megahertz is roughly the clock speed.
But is there some sort of overall synchronization in a quantum computer like there is in a...
Yeah. Yes, there also needs to be, so the signals that you're sending to them to do all the gates simultaneously, you also need to clock the electronics that you're using to send the signals. Yeah. Any other? Yeah, so copper has a much lower superconducting temperature. So the technology that we have, so these dilution refrigerators, don't get down to low enough temperature to actually use the copper have the copper be a superconductor. Yeah.
So, a computer can have feedback. It can store and feedback.
Yeah.
Does yours is more like just a wave?
Yeah, that's a great question, actually. So we can also do feedback. Instead of, let's say, for my dimmer switch, instead of sort of knowing exactly where it is, I can like sort of feel how far, like if I have a little diode or something, I can sort of feel some property of it so that I'm not collapsing it, but I know something about it. So I can use that to feedback and try to correct if anything goes wrong. So that's actually, in classical computers, is something known as error correction, right? If something goes wrong, you can actually look and see what happens. There's also an idea of quantum error correction where you look at the right things so that it maintains its superposition and does its processing. but you have enough information to know what to fix in your next cycle of processing.
Can you do things like work with imaginary numbers where things have to be sort of correlated?
Yeah. Yes.
For one more question? We have any more questions? Yeah.
Oh, I think it's still, so maybe I didn't say this during the talk. I don't think that as it stands now, quantum computers are gonna like replace the computers in your house, but they are gonna boost our ability to solve some important problems. And then so I think in 5 years, we might start to be able to simulate, we've already started to be able to simulate kind of easy-ish molecules. And then so maybe over the next 5 to 10 years, the things that we can, the like quantum systems and molecules we can simulate can get a little bit more complicated. But I think it's still going to be a research problem to figure out how to do feedback and how to actually build up a full-scale quantum computer.
For today, let's thank our speaker. And thank you all for coming to attend Saturday Physics for Everyone.